Now let's talk about the law of large numbers and central limit theorem. So first of all, let's talk about the weak law of large numbers. So let x1, x2 be a sequence of independently, identically distributed random variable, or IID for short, with finite mean exi equals mu. Because we have IID random variable, so this means ex1 equals ex2 equals mu, right? So all of the random variables, they all have the same population mean, mu. Okay, and they need to be finite. In other words, the mean needs to exist. Then the law of large numbers suggests that the sample average will converge in probability to the true population mean, mu. The weak law of larger number can be proved by the Chebyshev inequality. We don't have time to do the proof here. You can just Google that. Actually, you can just check Wikipedia. It shows a proof. But intuitively, it just shows. So intuitively, it's actually quite straightforward. It shows that the sample average x bar converge in mean square to the true population mean, and because mean square convergence is stronger than convergence in probability, so it can show that yes, the sample average converge in probability to the sample mean. It's called weak because the convergence is based on a probability limit. Okay, so there's a strong version of law of large numbers that is based on almost surely convergence. There's also a version of law of large number without the IID assumptions. It actually needs something called the stationary assumption that's used in time series data. Right? For example, if we have a time series of say GDP this year, GDP next year, apparently they won't be independent. Right? So if we want to apply law of large number to a time series data, then we need to make other assumption like the stationary assumption. In Econ 4A, we only deal with cross-sectional data. So we assume that the data are IID. So therefore, we can simply use the weak law of large number to get the probability limits. Next, let's talk about central limit theorem. It's the Lindeberg-Levy version of central limit theorem. Again, we have x1, x2 to xn, which is a sequence of independently identically distributed random variable, IID random variable. They have finite variance, so their variance needs to exist. We also needed to to center the random variable at 0, so their mean needed to be 0 for all I. So all of the random variable need to have the same variance, and all of their mean needs to be 0. Note that the mean 0 is not a restrictive assumption. Okay, it is just a normalization to center the random variable at 0. Okay. Then the central limit theorem suggests that the square root of n times the sample average converges in distribution to a normal distribution centered at 0 with variance b. What is b? B is simply the variance of xi. In general, xi could be a vector, so in that case, we need to write the variance xi as the second moment of the second moment, which is xi prime times xi. Right, so the xi inverse times xi. The variance, the B, which in general will be a covariance variance matrix, is necessarily positive semi-definite. Okay, that's the definition. The quadratic form must be greater or equal to 0. For our purpose, in econometrics, we the covariance variance matrix is assumed to be always positive definite. So the quadratic form must be greater than 0. So A, B, A prime needs to be greater than 0. In a one-dimensional case, then the B is simply the variance, which of course variance always needs to be greater than 0. In general, if we have a vector, then B is a covariance variance matrix. We need it to be positive definite. Okay. Like I say, just like the law of large number, there's also non-IID version of central limit theory, which often need stronger assumptions. Like in time series, if you want to get the central limit theorem to work in time series, you also need to make other assumptions. Now, let me quickly summarize here. The central limit theorem suggests that the square root of n times the sample average converges in distribution to a normal distribution with mean 0, and the variance is B, which is variance xi. And the law of large number suggests that the sample average converge in probability to mu, the population mean exi. Right. So notice that the central limit theorem actually converges faster than the law of large number. So people actually call this square root of n here the rate of convergence. Right? So the rate of convergence for the central limit theorem and convergence in distribution is actually faster than the law of large number here, because the rate of convergence for central limit theorem is square root of n, and the rate of convergence for the law of large number is 1. So in general, weaker form of convergence, like say the convergence in distribution, actually converge at a faster rate than stronger form of convergence, like convergence in distribution or almost surely convergence. Okay, and the central limit theorem actually converges at a faster rate than the law of large number. One implication here is that because we can apply both law of large number and the central limit theorem to an estimator, to sample average, so we can easily obtain the probability limit and asymptotic distribution for estimators that are linear functions of sample average. Right? So in fact, if we only want to get probability limit, even nonlinear functions of sample average is fine because of the continuous mapping theorem. However, if we want to get asymptotic distribution, because we know that the linear function of a normal distribution remain to be a normal distribution, right? So a linear function of sample average will also remain to be normally distributed. So why do we need asymptotic distribution? It is because we need to conduct statistical inference. And the reason we need to do statistical inference is because we don't have infinite sample size. Right here, we're all talking about asymptotics, but in real world, we will never have infinite sample size. So now let's talk about a definition. This is not a theory. This is a definition. So let's theta hey n is called square root of n asymptotically normally distributed if the square root of n times the estimator minus its probability limit theta converge in distribution to a normal distribution. And the V here is called the asymptotic variance. Okay, and we can denote that as A var, so it's just asymptotic variance of the. Note that this is the asymptotic variance. The asymptotic variance of the whole thing. Okay, so this is the V is not the asymptotic variance of theta hey, is the asymptotic variance of the whole thing here, the square root of n theta hey n minus theta. Okay. However, because we only have a finite sample in practice, we actually treat, so in practice we treat theta hey as if theta hey follows a normal distribution centered at theta with a variance v over n, and we call that the v over n the asymptotic variance of theta hey n. Okay, and we sometimes write, okay, the asymptotic variance of theta n hey is vn hey, the estimate of the true v over the sample size. And conventionally, we say that vn hey over n is a consistent estimator for the asymptotic variance of theta n hey. But what we really mean is that vn hey consistently estimates the whole thing here. Why is that? Well, notice that the true asymptotic variance is actually 0 for any consistent estimator, right? Because if let's say theta hey converge in probability to theta, and theta is not a random variable, right? That of course the asymptotic variance of theta hey is 0, right? Because when n goes to infinity, the whole thing will be 0, and that's how we say converge converge in probability to a non-random number, right? Because non-random, of course, there's no variance there. Also, keep in mind that theta hey does not have an exact normal distribution in the finite sample. The asymptotic property may approximate the finite sample property poorly. Right? What do we say here? Just say if n goes to infinity, then the theta, or at least when the sample size is very large, theta hey n, an estimator, should roughly follow a normal distribution. Okay, but that's an approximation. So it could be a good approximation or a poor approximation. Okay. So again, that's we are going to talk about a bit more later on the finite sample property of some particular estimators, like the OLS estimator or the IV estimator. Here we'll just introduce the definition of square root of n asymptotically normally distributed. Okay. Okay, so let's see an example, right? So we know sample average x bar is an estimate of the population mean mu. So let's check whether x bar is a square root of n asymptotically normally distributed. So how to check that? Well, so first of all, we need to write down this. Right, so it's the square root of n x bar. So x bar is our theta hat minus the peeling of x bar. Right, so to check whether x bar is square root of n asymptotically normally distributed, we write down like this, right? Square root of n times the estimator minus its probability limit. Okay. And by law of large number, we know the peeling of x bar is just mu, right? So we can, this is square root of n x bar minus mu. And then we rewrite x bar like this, right? It's just the summation of xi over n. And now we wanted to see, now we want to apply the central limit theorem. Here's a bit tricky, a small step we need to do, because to apply central limit theorem, we needed to standardize xi for the to make the xi to be mean 0. So we need this guy to be 0. So let's define. So let's just define zi equals xi minus mu. Apparently, it will be mean 0, and the variance zi will remain the same as variance xi, and let's call that sigma square. Then now let's rewrite the x bar in terms of z, right? So we know xi equals zi plus mu, and then that will be zi bar here times mu, right? This n times mu over n is just mu, right? So it's just here just zi bar or z bar plus mu. Then we plug in here, so we know that the square root of n x bar minus mu will equal square root of n z bar plus mu minus mu is just 0. And right, so this is just z bar, the square root of n z bar. And by the central limit theorem, we know that goes to a normal distribution with mean mean of zi, which is 0, and the variance of zi, which is just sigma square, right? Just here, right? So that shows that yes, indeed, because we can write down x bar as a normal distribution. Sorry, we can write down this guy, square root of n times x bar minus the peeling to be a normal distribution, right? So we show that yes, x bar, the sample average, is indeed square root of n asymptotically normally distributed. Okay, and in practice, with a large sample, large n, we will treat as if the sample average follow a normal distribution centered at the true mean, centered at the population mean, with variance sigma square over and over the sample size. Okay, right. So that's why we actually wanted to define this weird square root of n asymptotically normally distribution, because if we simply define on the estimate, say like x bar here, mathematically we will run into some problem, right? Because we know that when n goes to infinity, this guy must be 0. Then we cannot define its asymptotic variance, right? Of course, I mean, in practice, we treat this guy as x bar as the sample averages asymptotic variance, because in real world, of course, m is not infinity, but mathematically, it would be difficult to write down the relationship like this when you write down n goes to infinity, right? So that's why we define the relationship in terms of a square root of n. Okay. Also, there's also interesting implication here, right? Because we know when n goes to infinity, the variance of x bar goes to 0, which is confirmed that x bar is indeed converged in probability to the true population mu, right? So that's why when n goes to infinity, there's no variance. Okay. Right. So again, in general, we have this relationship here, right? We have a relationship here. We have square root of n times sample average converge in distribution to a normal distribution by central limit theory, and the sample average converge in probability to the population mean, right? By the law of large number. Right. So, in fact, that's because in fact here suggests that for sample average, it converges. So it converges to its probability limit at a faster rate than it converges to it converges to a distribution. Okay. So remember, so do not confuse central limit theorem with square root of an asymptotic normality. Okay, the central limit theorem is a theory, but the square root of an asymptotically normality is simply a definition. That's why in the previous example, we actually needed to show that a particular estimator is square root of n asymptotically normally distributed. Okay, it's simply a definition, so you need to show whether or not an estimator consistent with such definition. In fact, an estimator could be consistent or even unbiased, but not square root of n asymptotically normally distributed. Like in assignment 1, we construct an estimator, and that actually is not square root of n asymptotically normally distributed. Also, notice that the central limit theorem requires the mean of xi to be 0, not the mean of the sample average or the mean of the estimator to be 0. Okay, so let's say even if you have an unbiased estimator, like a theta here, it does not guarantee that the central limit theorem can be applied. Right? So you cannot simply say, oh, because Ex bar equals mu, so we can apply central limit theory directly to the x bar minus mu here, right? You say, oh, we cannot simply say, oh, this whole thing is mean 0. This whole thing is mean 0, so we can simply apply the central limit theory. Well, it's not that simple. We still needed to do a bit derivation here, right? Because the central limit theory actually require the thing in the summation to have mean 0. Right? It's just it's not very complicated, but you do need to do a bit of algebra to make sure that the mean of the thing in the summation needs to have mean 0. Lastly, the last thing we want to talk about this is, let's say we have two different estimator, theta head and theta's like what do you call it? Theta head and the theta squiggle. Both are consistent estimator and square root of n asymptotically normally distributed, and they have two different variants, two different asymptotic variants. Then we can say theta head is efficient or more efficient relative to theta squiggle asymptotically if d minus v is positive semi-definite. So essentially, intuitively, this means d is bigger than v, and of course, if the variance is bigger, then that means the estimator is less efficient. Right. The estimator with larger variance is less efficient. Also, we can say the two estimators are square root of n equivalent if the difference is small OP1. Right, so that means their probability limit is 0. Right, so if the two estimator, the difference is the square root of n times their difference is small OP1, then we say they are square root of n equivalents.